So we are very happy to have our own Raphael, and he's going to talk to us about singularity theorems from entropy bounds.
Thank you. All right, I'm going to start by plugging tomorrow's GeoFlow meeting. This talk was just an excuse. When do we start, Hugo?
10 a.m.
Okay, so it's very user-friendly, and you can find information on the GeoFlow website. Probably most of you are going to be getting an email or did already get one.
Yeah, also exactly. If you don't know what we're talking about, send a message. You must meet you now.
Otherwise, Google GeoFlow Berkeley. It should probably do the trick. We've got a wonderful set of speakers ready for you. So this is maybe a warm-up act. I don't know. All right, so the first part of this talk is going to be maybe a review for some of you. I don't know whether we teach singularity theorems in our regular GR course these days. I know it's hard to do that in a single semester course. So I figured that I'd actually go over Penrose's singularity theorem, because it is kind of useless to do this and not sort of see how it relates to what's been done before. So let's start with the definition of a singularity. It's very tempting to go into class mode and ask if somebody remembers. But the answer is simply you let your manifold M be inextendable. That's just so that you don't have any stupid singularities that come from the fact that you made your manifold smaller than it could have been. Right, so it is not a subset of a proper subset of another manifold. Okay. So then the usual signature that in GR textbook is defined as a singularity is an incomplete time-like or null geodesic. And incomplete means that it has no endpoint in some direction, either past or future, but only finite affine parameter range. Or if it's a time-like geodesic, we could just choose proper time to be that affine parameter, starting from some point in the space-time. So your classic examples here are, of course, the singularities that we all know and love. So here's a collapsing star. Maybe it's can be approximated as a ball of dust. And then this would be an example of a time-like geodesic that starts somewhere in the space-time, and it takes only a finite amount of time for it to reach the singularity, meaning it can only be extended forward a finite amount of time in the manifold M with metric GAB. And then, of course, there's also null geodesics which are incomplete in this space-time, like this one and that one, and so on. Okay, and then another classic example would be cosmology, of course. So this is, I'm going to try to make my singularities wiggly. This is a Friedmann-Robertson-Walker universe. I've chosen it to be spatially flat. So this would, for example, be a slice of what would normally be called constant time, meaning constant density in the universe. Here, observers, if you follow them in the past, they began a finite time ago. So that's another example. Okay, that's now, this is not a perfect definition. There are things that you'd like to say are singular, which are not captured by this. But and it doesn't tell you very much about why the space-time cannot, or why these geodesics can't go further. For example, an interesting question is to relate this to some curvature invariant blowing up. It's not perfect, but it has the advantage that it's the kind of thing that can be proven by theorems. And it does sort of capture at least one sufficient condition for when you would say it's singular. Like if your world line can just end after a finite time, that's weird. Okay, so good. A real landmark, I think, in the development of modern general relativity was Penrose's singularity theorem. It was kind of the beginning of modern global methods as applied to GR. And it's extremely satisfying to note that he got a Nobel Prize for it a mere 55 years later. For other things too, but I think this was kind of a key accomplishment. And so let's just briefly review this theorem and how it's proven. So what I want you to think about as a specific example, let me just erase these guys for a moment. As a specific example, I'd like you to think about a surface such as this one here. And notice that the exterior of this surface, so if we think of this as dividing a Cauchy surface into two parts, the exterior is non-compact. Okay. Another such example would be this surface here with respect to this exterior. Okay, so all right, the other thing that these surfaces share is that they are trapped, or more precisely, this one here is trapped. And this one here is what is called anti-trapped. And as you'll note, that's why the singularity here is in the future, and here it's in the past of the surface. And we'll just review what this means. What really matters here is actually only this direction. So if you look at the light rays that come out orthogonally from this surface, they have the property that they have negative expansion. This is very simple. The spacetime is spherically symmetric, so you can just sort of see that the spheres are getting smaller in this direction. This is not what happens in Minkowski space when you have a sphere and you sort of look at the light rays going off into the non-compact direction outside of the sphere. Then, of course, the sphere would grow. So it's natural to think of this as maybe a signature of something about to go wrong, right? And similarly here, what Penrose's theorem really cares about is this. Are these light rays orthogonal to the surface? So let's call this thing L. And it has theta less than 0. So the theta here is taken to be the light rays that expand into the interior of a non-compact region. But normally what you would call the exterior, since it's non-compact. Okay. Good. So the statement of the theorem then is the following. So we have a manifold with metric GAB, manifold M. And I'm not going to repeat these a whole lot. There's a bunch of boring assumptions, like it needs to be globally hyperbolic, connected, if you want to worry about certain weird things. And the null energy condition should be satisfied, meaning what I really mean is it satisfies the Einstein equations with the stress tensor contracted with any null vector like so, never being negative. Of course, this is a limitation in the real world. There are quantum states that violate this. We'll get back to that. Okay, so let T be an outer trapped surface. Meaning that theta of the light rays going to the future and into T, that those light rays have negative expansion. Okay. And what we also want is that the exterior of T, by this I always mean, I won't spell it out, that we think of T as dividing a Cauchy surface into two pieces. I don't care about the interior, whether it's compact or not, but I want the exterior of T to be, sorry, when I said into, I want the exterior of T to be non-compact. On a Cauchy surface that contains T. Okay, so those are the assumptions. I think that's, yeah, and I haven't quite, well, I told you what outer trapped is, that these particular expansions are negative, and the outer just refers to the fact that the light rays are expanding into a non-compact region, which is often associated with the outside. But if you don't like that word, this is just the definition. And the thing that I won't write down, but it's also important, is that T itself is compact. That's well, maybe it's important enough that I should have written it down. And by surface, I always mean a spatial surface, something of codimension 1 + 1 in the space-time. Okay. Okay, it also has to be smooth and so on. I mean, the technicalities, I won't have time to. So it's worth understanding at least the basic structure of the proof of this theorem. And then obviously there's a time reverse version of this theorem that would apply, for example, to this Big Bang case. Oh, I didn't write down the conclusion, though. It's kind of good to write down the conclusion. Sorry. So then, at least one of the null geodesics in this congruence, the guys that we're worried about, whose expansion we're worried about, is incomplete. So there's a singularity. So in the interest of time, I'll try to cut this a little bit short. But the basic idea here is, let me add a spatial direction and draw T like this. And to actually get to the conclusions that I want, this is the non-compact side now, okay? Except it will arrive at a contradiction, obviously. So the light rays that I'm worried about are the ones that go into that region, right? And they look like this. Let me just draw them. Okay. So they have theta equals 0. Theta less than 0, starting out here. Okay. And the null energy condition guarantees that it stays that way. In fact, it guarantees something stronger. So the Raychaudhuri equation tells you how these light rays, how the expansion evolves. If lambda is the affine parameter, then this holds. So theta is the expansion, sigma is the shear, and this term here has the stress tensor in it, contracted with a null vector that's tangent to these light rays. And notice that these things are positive. or 0. So it follows that that this is true. And you can prove from that the classical focusing theorem, which has these letters. Okay, so this, yeah. So now for simplicity, let me just make a simplification here. Okay, since we assumed that theta was less than 0 everywhere on T, and since we also know that T is compact, that means that theta is actually bounded away from 0. It can't approach 0 arbitrarily closely anywhere on T. Right? That means, in turn, that I can just rescale my affine parameter so that theta is always the same everywhere on T. For example, I could just make theta equal -1. Okay. So in that case, if you look at what this equation tells you, I'll put some dots here so that you don't confuse it, is that theta has to approach -infinity at or before lambda equals 2. Okay, theta equals -infinity, that's something like this. More generally, it would be what's called a point conjugate to the surface T, which is where infinitesimally neighboring geodesics intersect. Okay. Okay. So now I'm going to define a set. Well, I'm going to write it in words. The set consists of all the points on geodesics, the null geodesics that we're worried about here, with lambda in the closed interval 0, 2. Okay. Now, at the latest here, I will assume for contradiction that the geodesics are complete. All of these geodesics are complete. In particular, it's enough actually if I make the weaker assumption that all the geodesics at least extend to lambda equals 2. If I make that assumption, and only if I make that assumption, then this curly L is the image of a continuous map from, well, the surface cross the interval 0, 2 into the manifold. So generically, what L would look like is something like this. So L would be this whole thing. Right. We don't care whether there are any caustics along the way. We keep going if we need to. We go until lambda equals 2. Okay. Now, this here is a compact set, since T is compact and this interval is. So L is compact. This is very important. Okay. Now we're going to define another set called normal L, Okay, and it's going to be the boundary of the future of the interior of T, which is the same thing as the Cauchy horizon of the exterior of T, which is this thing here. Okay. So for example, if this is the interior of T out here, right? If you look at the future, well, those are the light rays that are going off, or these are, well, the future looks like whatever is outside this green cone, right? The future of this exterior. And the boundary of the future is precisely the green cone, because any point in here is indeed in the future of the exterior of T. Okay, so good. It's going to be important later that L is a light sheet in the sense of the covariant entropy bound. But right now, this is just a definition. Okay, so there's some theorem, some GR theorem, that says that any set of this form, the boundary of the future of some partial Cauchy surface, is closed. So, I don't know, somewhere in chapter 8, I think, of Walsh, for example. Good. But now it's important to note that geodesics, these geodesics that generate L, I mean, again, I'm sort of maybe obvious, I'm not proving here, but L consists precisely of the geodesics that come out of T and that we're worried about here. They're orthogonal to T, null geodesics. And you could ask, when does such a geodesic leave L? Well, here's an example, when they all meet each other. More generally, geodesics leave L at any conjugate point. So of course, that's not going to be the same point for all geodesics. More generally, it's going to be some ugly shape with, and also at self-intersections, which are not at non-local self-intersections. But that doesn't matter. Certainly at conjugate points, they leave, and that's all we need here. Okay. So geodesics leave L at or before. I'm writing at or before because, again, there are other ways that they could leave conjugate points. And as a result, since we have defined curly L to contain all the conjugate points, for every geodesic, it has to go through a conjugate point while it's still on curly L, assuming that these geodesics are complete. That means that L is a subset of curly L. Okay? Right, and that in turn means that L is so if you have a closed subset of a compact set, then that subset is compact. Okay, that's just a basic theorem in topology. Okay. Okay, now morally what this means, so there aren't any holes in L, in normal L. What it means is that the exterior of T, sorry, this is the interior of T. Yeah, the interior of T together with L is just as good a Cauchy surface as this was to start with. This is the part that's actually, you have to be very careful about exactly how you actually prove this. You have to define some homomorphism that maps L to this region and show that the image is both open and closed, and therefore it has to be the whole thing. Okay, so I won't go over that since it's tedious and we don't have infinite time. But the upshot is that that the exterior of T is also compact. So this is really, I'm leaving out a few details here, but I hope it's intuitively clear. Okay, and so then we have a contradiction because we assumed that the exterior of T is non-compact. Okay. Good, so that ends the sort of review of Penrose's theorem part. So if there aren't any questions, then I will get to the part where we try to derive a singularity theorem from a somewhat different starting point, the covariant entropy bound. So what the covariant entropy bound is going to do is it's going to replace the non-compact assumption, roughly speaking. Okay. And I will discuss two versions of this story. One involving what you might call the classical covariant entropy bound. So this is fairly old work by myself. And then at the end of the talk, I'll discuss briefly what the implications are of a sort of quantum-corrected version of the covariant entropy bound in the same context. Okay, so just lightning review. Take some surface like this. Consider a light sheet of that surface. That means that we need to have theta less than or equal to 0 away from the surface that we're starting from. The surface maybe has area A start. Okay, because the expansion is negative or 0, and by the null energy condition can only decrease, this final surface here that I've chosen arbitrarily has area A n less than A start, or equal, I guess. And this thing here is called the light sheet. Okay, so it's the null hypersurface generated by these non-expanding light rays. And now you imagine that there might be some matter systems, boxes of radiation, a cup of tea, and these are their world tubes, I suppose. And I'm in a regime where I have good control over the sort of vacuum subtracted entropy of these objects. I know what their entropy is. I'm not confused because there's just a single photon maybe that's bigger than this entire region I'm looking at. It's a clean situation where I know what the entropy is. I know what the area is. It's very classical. And in this situation, the covariant entropy bound tells me that the entropy on this light sheet, in other words, what counts, by the way, here is this one and that one, but not this one, right? Because this one goes through the hole here. It doesn't actually register on the light sheet. So we're going to add the entropy of these two matter systems in this particular example. That's what we mean by S of L. And it's bounded like so. Okay, so that's the review. Any questions about that? So this is, of course, a conjecture. By now, it's, I think, fairly well supported. But in exchange for trading this non-compact assumption for this conjecture, we'll get something nice. In fact, what we'll be using here is only the case where A n is 0. In other words, where the light sheet really does close off. Yeah?
Can you remind me, how do you define the entropy just classically? It's through the equation of state of the matter or something?
No, just if I tell you what is the entropy of a box of radiation of this volume at this temperature, what is the entropy of 200 particles that you don't know what their spin is, in that sense. I mean, you can try to be more precise by defining a vacuum-subtracted entropy, for example. So within the context of quantum field theory, which I'm trying to avoid, you could define some vacuum-subtracted entropy like so, but that doesn't always work very well if gravity is strong. Which is why this bound is sort of really well defined only in situations where gravity is classical, and the matter systems are well isolated matter systems, or admit a sort of hydrodynamic description of entropy, like we often, in cosmology, we would say, so this is some expanding universe, and we kind of know what we mean by the entropy in a large ball-shaped region. If this is dominated by radiation, the entropy density, which is the entropy per proper volume, is going to be of order, is some order 1 factors, the energy density to the 3/4, I guess, times the number of species. And yeah, so in that situation, you'd know that. Yeah, that's right. That's right. But for example, that breaks down when you look at a region that's smaller than the thermal wavelength of these things. So you don't. The quantum version of the bound doesn't have any of these annoying limitations. All right, so I'm going to make the same assumptions as here. M and GAB is globally hyperbolic, satisfies the null energy condition, and the same assumption about B being. So, sorry. My focus will now switch to calling. So this region X, that's going to be now called B. Okay. I'm no longer going to require that it's non-compact, but it plays the role of this non-compact region, right? So so first of all, these assumptions about M and GAB, and now we're going to let B be a partial Cauchy surface, what we would colloquially call a region at some instant of time. And we again need it. So this T is now the boundary of B, right? So that's the thing we're going to require should be compact. And we now care what the area of this boundary is. And what we also want about B is, again, this property. Okay, so by this I mean the null geodesics orthogonal to this boundary should have classical expansion that's negative. In which direction? Well, the important thing is that it goes into B. Okay, that's before we were also going into the non-compact region. Now we just go into B. What I don't care about is past or future, but let's just say future directed. Otherwise, you get the time reverse theorem. So here, I mean, specifically here, my conclusion would have been, of course, future incomplete. But if I trade outer trap for outer anti-trap, would have been past incomplete. Okay. Okay, I'm deliberately not being overly specific, but in the sense that you sort of asked about, I want SB to be the entropy of matter in B. So again, if you know the entropy of a bucket of water and of a box of gas or whatever, add them all up if they're in B. And what else do I want? Nothing. Okay. Now, what we're going to assume is the covariant entropy bound. Okay. Then the claim is that if the entropy in B is greater than the area in Planck units of the boundary of B, then at least one null geodesic that are orthogonal to dB in this particular direction where we're going to the inside is incomplete. Okay, and the proof is actually very simple because very few things are modified compared to the proof of the Penrose theorem. Okay. So let's just quickly write it down. And feel free to interrupt. You guys are not asking too many questions. So the thing that doesn't change is if we assume that these geodesics are complete, then the light sheet L which is the Cauchy horizon of B, or the boundary of the future of the complement of B, just like we discussed earlier, is a subset of the set curly L that is defined to be the points that are found by these light rays if you extend them to the affine parameter by which they're guaranteed to have met a conjugate point. Okay, so the point is here that this assumption is the same as before, and that's the assumption that gives you all that stuff. Right. It's just that this expansion is everywhere negative. It also means that this L is a light sheet so that I can apply the covariant entropy bound to it later. Right.
So Raphael,
yeah.
these pointers, you assuming the no energy condition.
I am.
Right? Okay.
Yeah. For example, if I didn't assume the null energy condition, then the fact that the expansion is initially negative would not guarantee that it stays that way. That's right. We're going to drop that only when we get to the quantum version of the covariant bound. Okay, so that means, as before, that L and B are both Cauchy surfaces of the domain of dependence of B. So this is the same picture that we already have up here. Right? And of course, if I have a domain of dependence, it looks like this, right? And any Cauchy surface here will have the same domain of dependence. It will have the same information. It's unitarily equivalent. So it has the same entropy. Nothing new can come in between these two slices. Nothing can go out. It's the same stuff, right? So, so this means that S of L is the same thing as SB. And now we have a contradiction with a covariant entropy bound. Okay. And this was kind of easy, right? There was little to it. It's worth going through some examples to sort of appreciate what this can do, and in particular what it can do that Penrose's theorem could not do for us. So let's do some examples. So my first example is a flat Friedmann-Robertson-Walker universe. We've seen this diagram before. And let me start by making some contact with Penrose's theorem. So let me consider this region, B1, which is non-compact. Okay. Now, if this is dominated by radiation or dust, there's some sort of division here into, this is an example for dust, into regions which are normal, meaning that the light waves contract towards r equals 0, and a region which is anti-trapped. So for these spheres, the light waves contract towards the Big Bang. And as you'll see here, on any constant time slice, sufficiently large spheres will always be anti-trapped. So I'm assuming that this is one of those. And so this is a, well, according to Penrose's theorem, this is a bunch of light waves that are contracting and going into a non-compact direction. So the theorem triggers and says there has to be a singularity, and indeed there is. According to this theorem, well, this is an infinite amount of entropy. So it's certainly bigger than the area of the surface. And this is still contracting, so same conclusion. Okay, so they both sort of detect this, this singularity. All right. What's interesting is that Penrose's theorem would not have detected a singularity if we had started from the region B2. Okay, so the region B2 is compact, and it has, well, if I make it large enough, then it'll be true that the entropy in here will be greater than the area, because these constant time slices are just flat Euclidean three-dimensional space. So if the entropy density is constant, the entropy in a ball will grow like the volume, the area like the area. So sooner or later, entropy wins. And so the theorem would diagnose the singularity also starting from this region. Now you could say, okay, fine, but Penrose would have told me by just looking at the complement region. And that's okay. So there's not much of a difference here. What's more fun is to consider a closed universe, because of course that contains no non-compact region, so Penrose's theorem never applies. And just for definiteness, let me assume that it's dominated by by radiation. Turns out that in that case, the diagram is square with a Big Bang and a Big Crunch singularity. These lines here are the north and south pole of the three spheres which expand and then collapse. And the structure in terms of trapped and anti-trapped looks like this. So these are the contracting directions. So if I choose a region B3 down here, like so, then I can arrange, for example, I can just start with a region that I was considering over there, like B2. But then it turns out I lied to you. This is not actually a flat universe. There's a tiny, tiny amount of curvature that you wouldn't even have guessed about by just looking at B2. So on a very big distance scale, the whole thing just closes off. Shouldn't make a difference. According to Penrose, well, what it does is it spoils the applicability of Penrose's singularity theorem. Physically, of course, it makes absolutely no difference if this thing closes off at large distances, right? And so one nice thing about this theorem is that it also really doesn't care. So it will still detect this singularity. Maybe an even nicer example is de Sitter space, which is also a closed universe, or at least we can view it that way. So here, these things are not singularities. They're past and future infinity. But these are still three spheres. And as you may remember, so a nice embedding diagram looks like this. So these three spheres contract exponentially, really like a cot, and then expand exponentially in the distant future. So let's start with that, okay? And now let's take a hemisphere at very late time and sprinkle it with radiation. By sprinkle, I mean that I'm going to add some radiation whose density is much smaller than the vacuum energy density. So that I'm really not, I can change the metric here in the initial data seemingly by an arbitrarily small amount. I mean, I have to correct a little bit for the back reaction from this radiation, but I can make that as little as I like. Okay. Good. Now, so let's call this B4. I want this to be a hemisphere just for simplicity. We know that in de Sitter space, this here is an anti-trapped region, and this is a trapped region. Cosmological singularity theorems don't apply here, so you have a trapped region. But for example, Penrose's theorem or other cosmological singularity theorems will not tell you, correctly will not tell you that this leads to singularity. Because, well, de Sitter space is clearly a good solution. They better not tell you that, right? Even though this is trapped. Why? Because there are no non-compact regions. But it's actually very easy to get a singularity in de Sitter space if you add too much radiation. What happens is when you add a lot of matter up here, even if it's very dilute, it gets exponentially condensed as you run the equations of motion backwards. And so it can create a Big Bang. Right? And this theorem can diagnose this. So what can happen is that there's a Big Bang actually here. This could be an arbitrarily large amount of time in between. But the theorem will diagnose it if simply the entropy in B4 is bigger than this area. And you can see that we can easily arrange that. Right? So the entropy in B4 is the energy density of the radiation to the 3/4 times, well, of order, times the scale factor cubed. The area goes like the scale factor squared. And so again, by holding fixed this rho radiation at whatever its tiny value is, so first make this as small as you like. Then holding it fixed, increase A. In other words, take B4 to be as late as you like. Right? So then I can arrange for this to be greater than the area the theorem triggers, and it tells me that there's a singularity here in perhaps a very distant past. So there's no analog of that kind of ability in the Penrose diagram, in the Penrose singularity theorem, excuse me. All right. I could go on. I mean, there's, of course, a classic example of a collapsing star. Again, for Penrose, it's very important that this region here is non-compact. What if it isn't? Well, it doesn't matter at all for the other theorem, because I can just choose this region here, B5. And if I choose it late enough, then the entropy of the star will be bigger than the surface area, because the star is collapsing to an arbitrarily small area. In fact, I can just choose this to be the time reverse of B2. That's how you construct solutions like this. You glue in the Schwarzschild to the exterior. You get a prediction of a singularity in the future. Okay. There are other solutions. For example, there are ones that are called monster solutions, where you have a black hole, and you put a big bag of gold behind it, for example. You can put a lot of entropy here. You can make that much bigger than this area here just past the throat. If this is a time symmetric initial data, then this will be contracting towards the interior, because spatially it is, and the time direction doesn't do anything. And so the theorem is again triggered. So it tells you that whenever you start with initial data where there's a lot of stuff behind the black hole horizon, or behind such a throat, to be precise, then you're going to get a singularity, so presumably it's also behind the horizon. Good, that's the end of the examples. Any questions?
Is there something that this says about cosmic censorship as well, this construction of singularity?
Yeah, I mean, that's the assumption that these singularities will be hidden behind the horizon. So when I said presumably, what I meant is assuming the cosmic censorship projection.
This construction doesn't guarantee that, right? I mean, this would be an extra assumption, or maybe.
Yeah, it doesn't. Yeah. If you want to get from singularity to behind the horizon, you need cosmic censorship.
Sorry, quick question. So in the center example, if you add in sufficient amount of radiation, you can get a singularity. But if you don't, then you don't. Sorry, how does one see this from the proof of your of the singularity theorems using the covariance rebound?
Well, so first of all, it's important to note that not every surface that has the property, or not every region that has the property that the future-directed light rays orthogonal to it end in a singularity will satisfy the assumptions of either of these theorems. So the claim is not that they diagnose every instance. And so in particular, I would expect that I will have examples. There should be examples where I don't put quite as much entropy on the sphere, and it will not predict a singularity. This also has to do with the fact that, violations of, there's kind of a gap between how much entropy you can generate with matter in most circumstances and the Bekenstein-Hawking entropy. So there's going to be examples where this doesn't diagnose a singularity. I'm just claiming that it diagnoses it in a whole new classes of examples. But the basic intuition for the de Sitter story is that, you got to run back with this exponential contraction. And if before the would-be time of the throat, the radiation density has become bigger than the vacuum energy density, then this becomes a closed radiation-dominated universe, and there's going to be a singularity. The vacuum density doesn't matter anymore. So the next thing that I want to just say is these things are not as disconnected as they may seem. So there's at least a heuristic argument, not as rigorous, I would say. The proofs are not as rigorous. The proof is not as rigorous. That says that the Penrose singularity theorem really follows from this one. This is sort of the stronger statement. What should we be worried about? Well, what we are worried about, right, is a situation like this, where we have a collapsing star. We have some non-compact region B. So the assumptions of Penrose's theorem are satisfied. It tells us that there's going to be a singularity somewhere along here. But the assumptions of this new theorem are not satisfied because I just said there's no entropy here. This is just vacuum. Yes, but if this is a non-compact region, I can add as much entropy as I like over here without changing the metric, or while changing the metric arbitrarily little, and in fact not at all over here. Okay, so I just add a lot of really soft radiation near infinity. So I can convert the initial conditions to ones that do trigger the new theorem without changing the metric. And so then there must have been a singularity here beforehand too. Okay. Good. Now, I don't have too much time left, kind of none, but fortunately, I don't have too many pages left either. And I think we're always merciful with Blackboard talks, right? I'm not hearing like huge cheering, but OK, I'll just keep going on. So the quantum covariant entropy bound is something that appeared in a paper by my student, Zach Fisher, Stefan Leichenauer and Aaron Wall and myself in 2015. That paper was really about the quantum focusing conjecture. Which states that the quantum expansion, the natural, well, good. It states an analog roughly of this classical focusing theorem, that the classical expansion cannot increase if the null energy condition holds, and the claim is that the quantum expansion cannot increase full stop in semi-classical gravity, so even if the null energy condition is violated. And the quantum expansion is just a variation of the, so for example, if I have some surface B here, I can compare its generalized entropy to the generalized entropy of some nearby surface that I get along a bunch of light rays. Usually I just deform in one place, actually. So I get it at different points. And I take a derivative per unit area. That gives me the quantum expansion. Now, the key thing here is that this object, the generalized entropy, is better defined than the entropy and really the area in Planck units itself, because the two terms sort of cancel, the RG flow of the two terms cancels. Right, so what this means is that if I have, so this is time as usual. This is some partial Cauchy surface B. Has a boundary here. And I'm looking at the quantum expansion of the light rays that are going sort of into B, let's say to the past, I don't care. And I want it to be true that right here at the beginning, the quantum expansion is less than or equal to 0. Then the quantum focusing conjecture keeps it that way. And by integrating up the change in the generalized entropy, we are able to conclude, let's call this other partial Cauchy surface down there B, little b, excuse me, that S gen B is greater than or equal to S gen little b, which is fine, but it turns out to be convenient to add to both systems a purification aux. So aux is an auxiliary system that purifies the matter entropy in the entire space-time M. So here's my space-time M. I don't know exactly what it looks like, but it has some Cauchy surface sigma. And then there's some other auxiliary system, which really could just be very far away, it'd be just as good, such that these things together are in a pure state. Okay, so I'm going to always include the auxiliary system as we vary. This is a little more specific than what this quantum bound really says, but that's the application that's relevant here. And just to give you an intuition for what this can do that the classical bound cannot do, before we get to the singularity theorem, is so for example, the classical bound will tell you that the entropy of the star is less than the area of the black hole that formed when the star collapsed, because this is a light sheet. Theta is equal to 0 here long after the black hole is formed. And so the classical bound tells you that the GSL, the generalized second law, holds. It implies the GSL for these sort of classical processes. Okay. However, if I consider the evaporation of a black hole, so I'm now in a quantum regime where the quantum and the classical expansion differ substantially, meaning that if I go to some time here where the classical expansion is actually greater than 0, because this black hole is evaporating, the horizon is shrinking towards the future. Right? It's not very much greater than 0, but it's greater than 0. I can't actually find a light sheet that goes down that way, right? This is no longer legitimate because in this direction, in this direction, the expansion is positive. I think I said it the wrong way. Right, so this is not a light sheet. But it is a quantum light sheet. But the generalized entropy is increasing towards the future, so it's decreasing towards the past. And so you can, in fact, apply. So for example, you could choose this to be B and this to be little b. And then the quantum covariant entropy bound would reduce to the generalized second law and tell you that the radiation that was produced since this time was more than enough in entropy to compensate for the lost area. Right. Okay, so the singularity theorem, the analog of this classical singularity theorem from the classical covariant bound, is again, we now get to drop the null energy condition. Here the null energy condition is violated. That's what makes the black hole evaporate. So let's just suppose that theta, the quantum expansion of the system B together with the auxiliary system, but evaluated at any point on the boundary of B, is strictly negative at all such points. And that this region B is, in a sense, hyperentropic. I should have used that term perhaps up there as well. So I want excuse me. Yeah. I want this to be true. So I put this gen in parentheses because if the auxiliary system is really outside the spacetime, then I don't need to add an area term. But if it's inside, then I'll add the area term. It'll contribute on both sides equally, so it doesn't really matter. So now the quantum covariant entropy bound implies a singularity. I won't write down that one of the generators, blah, 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 incomplete. Okay. And the proof is, again, just a modification of what we already have. The tricky part now is that you don't get to apply the classical focusing theorem to guarantee that your geodesics are going to have conjugate points and therefore leave the boundary of L after every one of them in finite affine time. But the only thing that you really care about is that they leave the boundary of L. And Walsh showed that a geodesic cannot stay on the boundary of the future or past if it has initially negative quantum expansion, or else there's going to be a contradiction with the generalized second law. Okay, so so he used this to prove some other quantum singularity theorem more than 10 years ago. And then, assuming completeness as usual, the rest goes through as usual. L must be compact, therefore. And in this, that's the same thing as saying that little b is the empty set. Okay. But then the quantum covariant entropy bound predicts precisely the opposite inequality from the one that I wrote down here. Okay. Good. So that's it. I want to finish with a puzzle, though. So this does all the things we wanted to do in a more controlled setting. In particular, it doesn't run into sort of problems that both the Penrose singularity theorem and this classical theorem would run into if I naively applied it into a situation where quantum effects are important. So for example, the apparent horizon, where the classical expansion is 0, goes outside of the event horizon. Okay. So I could have taken this region and applied either Penrose's, or take this region and applied perhaps this other singularity theorem to it, and I would have concluded that there's a singularity here. That's bad, and it doesn't happen if you include the quantum effects properly. So that's all nice, but there's some really bizarre prediction that this theorem makes in a situation where we think there is no singularity. Or I really think there's probably a sort of new class of singularity here. And the situation is very similar to the one that was considered by Pennington and by others. So that the auxiliary system, I imagine that we've taken the radiation out of the space-time, contain all the radiation that's been emitted by a black hole, and let this be our region B. We could have done this in asymptotically ADS if you prefer. And of course, it doesn't matter, again, if this auxiliary system, it just could really be literally the distant region that contains the Hawking radiation. Okay. To a good approximation, there's not much entropy in here. If this is sort of the time that corresponds to when these Hawking, before all these Hawking quanta were emitted. Sorry, after all these Hawking quanta were emitted, but not much after. Okay, so now we could look at this before or after the page time, but let's in particular look at it after the page time. Okay, so what do we know here? We know that this generalized entropy of B together with the auxiliary system is basically just this area term, because for the same reason that there will be islands, all of these Hawking particles that arrived here are sort of partnered with interior partners inside the black hole. There's a couple on the way right now, but let's neglect that. It won't be important. So this is just the area. And of course, the expansion in this direction is, quantum expansion is negative. And if we're after so this is always true, before and after the page time, but by definition of page time, after the page time, this will be bigger than the generalized entropy or entropy of the auxiliary system itself. Page time means that's the time when the radiation entropy is equal to the area of the black hole. So we're after that. So radiation entropy, which is this, sorry, what? The other way around. Thank you. Yeah. So the theorem applies. The theorem applies to these light rays. And yet, it's too bad the mask is on. You can't see just how puzzled I look. But I look very puzzled right now. Puzzlement. Because there's no singularity here. These light rays do, close off nicely and smoothly in the past. Yasunori, help us out.
Maybe not puzzle if you're saying that it's not the firewall shows up around the horizon, that's a singularity.
Thank you.
Then I think
This is nice that it's a talk where I don't have to start saying firewall. So where is the singularity, and why? Okay, so in my defense, I can say a couple of things. First of all, some sort of singularity is actually also predicted by Aaron Walsh's singularity theorem that I referred to earlier. His singularity theorem is a little different. He assumes the generalized second law, not the covariant entropy bound. And it applies to outer trapped or outer quantum trapped surfaces. So you still need this non-compactness that Penrose had to assume. But it does do the job of eliminating the null energy condition. So it's like a different part in a square. Like we've got 3. This is the 4th part. OK, so that theorem also, the assumptions of that theorem also become valid here. Because, for example, we know that there's an island that has the property that, let's call it I, that has the property that together with this auxiliary system, it is quantum extremal. Right? So that means that the quantum expansion is exactly 0 in all these directions, which means that if you go a little bit away from it, you can find a place where it's quantum anti-trapped. And it predicts a singularity somewhere along those light rays. So somewhere here, there seems to be a singularity. Unless both of these theorems are wrong, which means that the generalized second law and the covariant entropy bound are both wrong. And so is the quantum focusing conjecture. So that's one possibility. Now, another possibility is that we're doing something wrong in the way we're calculating the entropy. Maybe, as you follow the generalized entropy back, when you need to sort of impose smaller and smaller. I mean, you need to impose a very small cutoff here if you want to keep track of the change of the generalized entropy far down, because all these modes get contracted exponentially as you run back in time. The Hawking particles sort of have exponentially small wavelength here near the horizon. Now, that's no problem when you want to compute the quantum expansion, and you can. That's actually, there are models that, for example, AEMM and Pennington have in their papers, which tell you that the quantum expansion here is actually the same one. So the quantum expansion, if you want to look at the complementary region, is kind of how much generalized entropy does this have? Normally, we look at this region, the exterior of the black hole, right? And we say entropy is produced. In the radiation, the area is going down. It turns out that the quantum expansion is the same either way. So in fact, you run into a really big problem already before you get to this tip. The tip can't be that special. Moreover, the tip is really an artifact of spherical symmetry. We're used to sliding slices past caustics and past non-local intersections. They happen all the time. This tip is really everywhere. If this tip made any of these statements inapplicable, they would never be applicable in a generic situation. So when you actually look at what happens here, let me first of all draw the standard picture. So this is the area that the black hole started with, and it decreases to 0, right? This would be the entropy, according to Hawking, of the radiation. So that would be the same thing as S-gen. Sorry, that would be the same thing as S-ox, right? So this is time. All right. This here would be the generalized entropy of the complement of B in the space-time. So these blue slices, right? So I should have made them blue. Okay. Now this is the area of the black hole horizon over 4gh bar. But that's the same thing, right, as S of S gen B together with the auxiliary system. So now let's go to this time past the page time. There's no problem starting with this generalized entropy, that the normal sane blue slices have that we usually consider, and then computing the generalized entropy at earlier times by just integrating back the quantum expansion. Everything's fine. But if I do the same thing here, the quantum expansion is the same, so I get the same slope. But well before I get to the beginning of the black hole, and I can make this very much well before by just starting back over here, I formally get the answer that the generalized entropy is negative. So I suspect that there really is a problem with this backward evolution. And I won't claim that I know what the answer is in particular. I won't claim that my collaborator and I even agree on what the most likely guess is. But I think one possibility is that we're learning that a lot of the time semi-classical evolution behaves as though you were evolving with an ensemble of different theories. For example, that explains certain contradictions that the gravitational path integral leads to with factorization if you have two boundaries and you compute the partition function. It also resolves an apparent contradiction between the fact that the outstate of the Hawking radiation here is mixed, and yet Pennington's calculation tells you that the entropy follows Page's curve, which is this curve. In both cases, both of these things are consistent if you assume that what is being computed from the gravitational path integral is really an average over a suitable ensemble. The average entropy follows Page's curve, but the average state, well, the state's not self-averaging. You just get a lot of different outstates. They're all pure, so they follow Page's curve. Okay. Similarly here, this evolution that we're considering is really a backward evolution. Something that violates the second law in the ordinary sense of such violations. Meaning that if I have any kind of variation in the initial data up here, the backward evolution is not going to take me back to the same. It's not the evolution. If the gravity path integral computes an ensemble average, then going forward and backward in time doesn't get you back to what you started with. That's basically what I'm saying. And in particular, going backward in time, if this radiation is even slightly in the wrong state, you're going to get not only a firewall here, but you're probably going to get a white hole of some sort, and you get a perfectly good singularity that you can hit here. So that's my personal guess where this might end, but I don't think we're anywhere close to having a rigorous story. So with that, I'll thank you for your time and your patience. Thank you.